Okay, so solids of revolution. Okay, what this means is we are taking essentially, remember when we did this with a semicircle and we rotated it around the axis, making a three-dimensional shape? Okay, we're now going to do this with specifics and not with Riemann sums. Okay, we're going to use actual integrals. And effectively, we are putting a slice in here, right? And I'm putting an infinite number of rectangles in there, each one of those being pi r squared. 5, 4, 3. I need you guys at voice level 1 so I can teach this lesson, please. So, the beautiful thing about this is we have a nice formula. Volume equals pi. The integral from a to b, those are just x coordinates, of the radius function squared. Okay? That is going to be your formula. They give it here with the pi inside. I don't know why you would leave the pi inside. A lot of times you'll do the integration with these via calculator. You have to be able to do integration by hand because you don't get the calculator for the final. But this first one, the region under square root of x. The square root of x looks like this. And they're asking for the region 0 to 4 revolved around the axis, around the x-axis. That's important. We won't always revolve around the x-axis. Um, so I've got my slice. Pi 0 to 4 square root of x squared.
The streets and distance of word, and then it gave me paragraphs like basically down. So I just like, not.
I'll plug in my upper bound 4, 16 pi over 2 minus 0 pi over 2. So my answer is 8 pi. My three-dimensional shape, which I think they'll show on this next page, has a volume of 8 pi. That's not so bad, is it? So this is called the disk method. Okay? Now we find the volume generated by revolving the region bounded by the square root of x, the lines y equals 1, x equals 4, and y equals 1. So we're revolving around y equals 1. Instead of the x-axis, we're looking at this. Okay? This intersects at 1, 1. So pi integral from 1 to 4. My radius, though, instead of being square root of x for my y coordinate, it's square root of x minus 1. Okay? If I need to do this by hand, they foiled it out. Definitely the easier way. Okay? Does that make sense? Go ahead. If you're integrating and you got a squared, FOIL it out. Keely, voice level, and get onto your IA. and we get a volume of 7 pi over 6. We can see our figure looks like that. That makes sense. So we can revolve things around the y-axis as well. Okay. The key with revolving around the y-axis is, well, they usually are functions anyways, but it needs to be in terms of x equals y. My radius is then this guy. But my boundaries must also be my y coordinates. Okay? Not my x coordinates. Once in a while, that will throw you for a loop. Okay? But volume pi 1 to 4, 1 over square root of y squared. The squared actually works out to be nice in a lot of these, especially with square roots. ln1 is 0. So they did ln4 as 2 squared and brought the 2 in front. But so that's how they got 2 pi ln2. They're the same value. Any questions so far? This kind of makes sense. The abstractness of the shapes gets weird. Okay, this one's going to get weird. Find the volume of a solid generated by revolving the parabola x equals y squared plus 1 about the line x equals 3. So now we are revolving around a vertical line here. Remember that it's a vertical, so this is like a y definition. I'm revolving a vertical thing. So I need to use my bounds as my y coordinates. Um, my radius here is a little strange. Why did they do 2 minus y squared? Oh, I know what they did. So my radius is 3 minus my function. So this distance here is my function. That's y squared plus 1. My radius, then what I'm interested in, the total distance is 3, right? So this is the radius I'm interested in, 3 minus. Does that make sense? Which distribute the minus and you end up with 2 minus y squared. That makes sense. Then that must be squared. I don't really feel like integrating that by hand. I will probably leave this in terms of pi. So I'm going to go to my calculator. do my integral. Don't forget that extra squared. That's an easy thing to do. Okay, never mind. That's not a nice answer, so we'll just multiply times pi. 18.96. Okay, yeah, that look at their lovely answer. 64 pi square root of 2 over 15. I will let you do those on the calculator. I changed the numbers on the ones on the exam, so they're not necessarily nice, but they're not like that. Okay, so those are called disks. Essentially, we're slicing this thing into disks. Tomorrow we'll learn a shell method, which is different. But now we're going to talk about what's called the washer method. And the washer method is very much like when we did area between curves, you just did upper minus lower. The key here, though, is you cannot cross your axis of revolution with a washer. A washer essentially means you have this little cutout area. So it's like I have an upper and a lower, and my slice is here. Does that kind of make sense? So I got this hole in the middle of my thing. So what I do is I do the volume of this, the pink one, minus the volume of, can you guys see this orange? Volume of pink minus orange. And I do not square them together, I square them individually. So I would think of it more like I always pull the pi out because I think it's bigger. So big R being outer radius. This can also be done in Y. That makes sense? So we have the region bounded by y equals x squared plus 1 and y equals negative x plus 3 is being revolved around the x-axis. So here's my region. Notice that x, negative x plus 3 is on top. Okay? Does that make sense? So upper, this is upper. This is lower. My boundaries here, since I'm revolving around the x-axis, everything's defined in terms of x, are going to be my x coordinates. So pi, negative 2 to 1. This makes sense so far. I guess I should have made that a bracket like I did the other one. So we've got, look at my x coordinates on my bounds of the intersections. Um, you can find those by setting them equal. If I solve this, I get x squared plus x minus 2 equals 0. X plus 2x minus 1. So that would get me my -2 and 1. If you can graph it, you can just find the x coordinates. Um, it is important that you can see the graph because I need to do upper radius minus lower. To execute this, I don't feel like integrating that by hand. So I'm going to use my calculator. We'll see if I need to put in terms of pi. Actually, I can put the pi on the beginning. It'll probably leave it in terms of pi if it's decent numbers. Again, don't forget to square the entire quantities. It's very easy to forget, especially the second one. X 73.5. This must be very bad that it didn't give this in terms of pi. Yeah, 117 pi over 5. And I can verify that that's the same thing, but yep. I'll have your some. Yeah. Okay, is this all processing? It gets harder when you're not revolving around the X or Y axis. It gets harder when you have to do a washer. I think this is our last, yeah, this is our last example. So we're actually going to finish. So we have the region and it's revolved, region bounded by y equals x squared and y equals 2x, revolved around the y axis. So we can see this region right here. We've got a nice point of intersection here at 0, 0, and one up here at 2, 4. Now I'm revolving around the y-axis. So based on the methods you know, we want to solve this for y. Or solve it for x. I'm not doing plus or minus the square root of y because this is only the positive case. Okay. So as I do this volume, I'm revolving around y, which means I need y coordinates for my bounds. My upper, I have to look at it sideways and think of upper being further out from y. Minus lower. Yeah. This one I'm gonna just do by hand. That's y. This one is y squared over 4. This makes sense so far. Y squared over 2 minus y cubed over 3 times the 4 on the bottom. Sixteen over 2 is 8 minus 64 over 12. 16 over 3. That's 24 over 3. 8 is 24 over 3, so this is 8 pi over 3. I believe that is right. Yep. So doable by hand. Make sure you guys know how to integrate so you can do it on the final. But you are welcome to use your calculator for any of the integrals. If it's a bad one, just use your calculator.